Okay guys, today we're going to go through these three ideas: mass defect, the binding energy, and energy levels of the nucleus. Alright, so we're past the atom, we're not caring about electrons so much anymore, we're just talking about the nucleus, home of the nucleons. So mass defect, what people started noticing when they were fusing small things together in cyclotrons and things like that was that there was some sort of difference between the mass of the ingredients that went into making this nucleus, so the protons and neutrons, and the mass of the nucleus itself. It's kind of like when you stick some flour, eggs, water, and a whole bunch of sugar and butter and chocolate and whatever together to make a chocolate cake. The cake itself doesn't weigh as much as all the ingredients that went into making it in the first place. So there's this mass defect, so it's a loss or increase in mass. And if we lose mass, that mass has to be involved in some sort of system somewhere. So in this case, we're actually dealing with Einstein's most famous equation, E equals mc squared, where this m is this mass defect. So if mass is given off, so mass is lost in space, not really space, but mass is lost in the process of fusing small things together, what we're doing is giving off energy. If mass is needed to split things apart, so if the amount of mass at the end of the system is more than the amount of mass at the start of the system, we needed to put energy in order to create that. So there's this link that we can't get away from between energy and mass, so we're binding energy and mass. So it has to go somewhere. If we're losing mass, we're giving off energy. If we're gaining mass, we're using energy up, or it takes energy to do that. So this binding energy is defined as the minimum energy needed to split something, the nucleus, into all of its protons and neutrons, so all of its nucleons, so that they won't end up joining back together and at the end. So this binding energy is the amount of energy given off when you fuse small things together. It's the amount of energy given off when you split heavy things apart. This binding energy is related to the energy levels within a nucleus itself. So you can remember from the last stuff when we were talking about emission and absorption spectra, how we have, a whole bunch of energy levels for the atom. We've actually got energy levels for the nucleus, all right? And these energy levels are different for each atom or each element based on how much mass defect they had when they were bound together or built, I guess. So this might be the energy levels for, say, thorium. And it might be, so here's the ground, that's ground. It might be that the product that decayed into that was uranium, and its ground energy might be here. So it's actually got a little bit more, naturally in its binding energy. So when uranium decays into thorium, this alpha particle takes some of that energy, and it might take a tiny little bit of energy, and then we release the rest. So this release of the rest, gamma radiation. Just like when we're dropping electrons down back from excited state to the ground state, we're losing that energy as a series of photons or a photon. Here, just the energy is a lot bigger, it's still a photon, just in gamma radiation. Then we could have an alpha particle drops, is going a little bit faster, so it takes more of this excess binding energy with it, and it drops it down to there, and once again we get a gamma photon. Or it could be that the alpha particle itself was going really, really fast, and it took this much energy with it. So this alpha particle can exist in a few different states in this very abbreviated example I've given you here. It also means that this gamma particle, this gamma radiation, can exist in a few very discrete energy levels as well. All right. So just like the atom, the nucleus has them too.